Alright, we start this next video. We'll do like a little warm-up question on torque. So remember that torque is calculated by multiplying the perpendicular radius times the force. Okay, and so in this case we have somebody standing on the edge of a diving board. They're exerting a torque because they're pushing down on it, exerting kind of like this rotational force on it. They're 2 meters from that rotational point right here, the fulcrum, and so that would be our radius, and then this is the mass, okay, and so the force would be their weight. So given those two things, go ahead and calculate the torque exerted by this person. So you should have multiplied the radius of 2 meters by the force, which it was the weight, mg, so 150 kilograms times 9.8 meters per second squared. Okay, and we're going to end up with, so you should get about 2,940 newtons times meters. Okay, and so that would be the torque exerted by this person. Alright, and so right now, as we go through this stuff, these values for torque don't mean anything to us. They're just numbers at this point. Okay, and we've also talked about moment of inertia. We had these values that we got for those that also didn't mean anything for us. And so the next thing we're going to be doing is kind of putting all these things together. Okay, and so like I had mentioned before, torque is the rotational analog for force. Okay, and so let's look at Newton's second law. We did kinematics, and we did talk about Newton's laws. We said that the net force is equal to mass times acceleration. Okay, we're going to use the same equation, but replace all these values with rotational values. So the rotational mass is moment of inertia, or I. The rotational version of acceleration is angular acceleration. And torque is the angular rotational analog for force, and so we'll say that the net torque is equal to I times alpha. Okay, and let's just kind of show that those units are going to work out. Okay, so let's say that we have a uniform disk. Okay, and let's say that it has a radius of 0.1 meters. Okay, and let's say that it has a mass of let's say 2 kilograms. Okay, and the question is, how much torque would be needed to accelerate it at a rate of 2 radians per second squared? Okay, so given all this, so torque, the net torque, will be equal to I times alpha. Okay, well, we know alpha is 2. Okay, we need to find our I value, our moment of inertia. If it's a uniform disk, we look here. Okay, moment of inertia, this would be for a uniform disk, okay, or a cylinder, 1/2 mr squared. So I equals 1/2 mr squared. Alright, that's 1/2 times 2 kilograms times 0.1 meters. That's going to be squared. So that gives us 1 times 0.1 squared, or 0.01 kilogram meters squared for I. Okay, so if we plug it in here, we have 0.01 kilogram meters squared. Okay, we're going to multiply that by 2 radians per second squared. When we multiply meters squared times the radians, then the radians disappear. So we get 0.01 kilogram meters squared per second squared. Okay, which gives us 0.01 kilogram meter per second squared is a Newton, and then we have the 1 meter on the outside. okay, which is our units for torque. Alright, so the torque required to rotate this disk at a rate, or accelerated at a rate of 2 radians per second squared, would be equal to 0.0, oh gosh, math error there, okay. So 0.01 times 2 would be 0.02, would be 0.02 newtons times meters. Okay, so, the next thing I want to point out though, let's say that we wanted to have an angular acceleration of 0. We wanted to rotate at a constant speed. Well, if alpha is equal to 0, then the net torque also equal to 0. So for something that's rotating at a constant speed, that means the net torque on it is 0. Just like if you have something sliding or moving along at a constant speed, it has a net force of 0. Okay, so here's a net torque question for us. We have a seesaw here with an elephant on one side and a mouse on the other side, and we want to know how far away the mouse would need to stand to balance out the elephant. Okay, we have the mass of each of them. Okay, we have the radius of the elephant. Okay, and we can actually go ahead and figure out that distance for the mouse. Okay, well, just like we do with Newton's laws, we're going to say that the sum of the torques is equal to I alpha. Okay, that would be equal to the force from the elephant times the elephant radius minus, so this is positive because it's going counterclockwise, so then minus the force from the mouse times the mouse's radius. Okay, now since we want it to remain in equilibrium, this will be equal to 0. Okay, the force from the elephant would be the weight of the elephant, so we'll use big M for the elephant's mass. Okay, so mg times r for the elephant minus little mg times r for the mouse. Okay, we add that over. Little mg r equals big mg r. Okay, and g will cancel out. We divide over little m, and the radius of the mouse would be equal to big M times r sub e over little m. Okay, go ahead and punch it in, and let's see what we get. So 4,600 kilograms times 10 meters over our mass of 0.025 kilograms. And then we get a distance of 1,840,000 meters, which is 1,840 kilometers. Okay, we can say that about, so that'd be about, trying to do a little conversion in my head here. So that would be about 1,100 miles away that the mouse would have to stand in order to balance out the elephant. Okay, that's about the distance from here in Southern California all the way to Texas. Okay? Okay, so here's a practice question. We have a cylinder. Alright, there's two forces acting on it. It has an axis about its center. Okay, we have two forces pulling on it, one with a force of 120 newtons, the other with a force of 60. Okay, the cylinder itself has a mass of 90 kilograms, and the question here is, what is the acceleration produced by those two forces? Okay, so if you think about it, one's kind of pulling it this way, this one's pulling it this way. You have a positive torque from this one because it's going to cause it to rotate counterclockwise. This one is pulling it the other direction, trying to make it rotate this way. Okay, and so the question is, well, what is the rotational acceleration? So this tells us we want to find the sum of the torques, and they should be equal to I times alpha. Okay, and we'll call it T1 minus T2. Okay, and this is a cylinder, which means that I would be equal to 1/2 mr squared. I'm also going to point out that both of these are perpendicular, so you only need to multiply the force by the radius. Okay, now I want you to take a minute and pause the video and see if you can figure this out on your own. Okay, so let's go ahead and do this. We'll substitute in values here. 1/2 mr squared for I, F1R1 for T1, F2R2 for T2. Okay, so 1/2 times 90 kilograms. The radius of the circle is 0.12 meters. We'll square that. We have alpha right there. Then over here, it's going to be 120 newtons times 0.12 meters minus 60 newtons times 0.08 meters. Kind of gone ahead and done the rest of the work, so we subtract, we get 9.6. We take our moment of inertia, divide it over, okay, and we get that the angular acceleration is 6.22 radians per second squared. And let me just show you how these units work out. So the torque is newtons times meters. We're dividing that by moment of inertia, which is kilogram times a meter squared. Okay, one of those meters cancels out right there. Remember that a newton is a kilogram meter per second squared. That's all over kilogram times meters. Okay, and so this meter is going to cancel with that one, the kilogram is going to cancel with that one, and we're left with 1 over second squared. Okay, and I'm not going to get into why there's the radians here, but it is radians per second squared. Okay,